All right.
So we are recording now. Okay, great. So let's take a look. What does this say? Unmarked police car traveling at a constant speed of whatever miles per hour. I don't know, let's call it 75 miles per hour. Precisely 1 second after. So they're passed by a speeder. Precisely 1 second after the speeder passes, they accelerate. Okay, so what this is saying is that the car is already moving, so this is the cops. And then the other speeder, it seems like we're assuming that the speeder is moving at a constant velocity themselves. So let's call them VS, the velocity of the speeder, right? So it's going to be faster than whatever the cop is moving as. I just made up the 75 kilometers per hour. And it says a second after the speeder passes, the officer steps on the accelerator. So, okay, let's basically define T0 as the time when the speeder just passes the car. So they're at same position. And T1 is equal to 1 second later when police starts accelerating. Okay. And now it says that their acceleration is some given. Oh, I don't know. Let's call it 3 meters per second squared. And overtakes. And we're also told overtakes the speeder after however many seconds of accelerating. So I don't know. Let's call it 10 seconds of accelerating. Let's just figure out how to set this all up. So the condition is that at the very end, they both have the same x position, right? So when they catch up, x of the police car is going to be equal to x of the speeder. Yeah? And we basically just got to figure out two ways to... I'm trying to think of all the unknowns that we have right now. Do we know time? We do have the time, right? Overtakes the speeder after accelerating for 9 seconds. Okay, so that's sort of our hint to use the x is equal to v naught t plus 1/2 at squared equation rather than the vf squared minus v naught squared is equal to 2ax, because we have the acceleration in both. We have the time over here, and we have the v naught. So, this will make it easier to find x of the police car at the end, as opposed to having to go out of our way to find velocity final. Because over here, there's two missing variables, right? X and the VF, so we would have to use more equations. So that's why I'm motivating that this is probably the equation to use, at least to describe the cop car. Does that seem reasonable? Okay.
Yeah.
So what did I call it? I called, let's say that this is the V of the police. Or let's maybe call it V naught of the police. Okay. So V naught of the police times, what was the given time? 9 seconds.
Mm-hmm.
Or was it 10 seconds?
Yeah, on your question, it was 10 seconds.
Let's see, how do we account for this? Yeah, so the one thing a little bit strange about this question is that I need to work in the extra bit of time, the 1 second during which the cop was just speeding before they accelerated.
Mm-hmm.
But to do that, let's say T2 is equal to when the cop catches up. And that's basically at 11 seconds. So I like writing it this way, T0, T1, and T2, because it really sort of explicitly outlines the phases of the question. But I'm going to write this as T2 minus T1 plus 1/2 a T2 minus T1 squared. But I'm also going to have to add the extra second from before the cop started accelerating, right? So that was, what was that, t1 minus t0? And that was times the cop's initial speed. I think that was just v naught p, right? Does this equation make sense so far? So assuming that x is equal to 0 is at the very start of the problem when the two of them are side by side, the kinematic equation describing the cop's car is going to be xp is equal to, this stuff is describing the distance gained during the accelerating phase, and this is describing the distance gained during the non-accelerating phase. Does this make sense so far? Okay, great. Right, and this is just a tiny modification of the equation because this is kind of atypical, right? This problem is broken up into accelerating and non-accelerating phases, but really, hopefully it shouldn't be that confusing, right? If I wanted to break this up even more, I could have expressed this as two separate equations where I could have said like xp1 was equal to, this phase, and then xp2 was equal to the accelerating phase. But I'm hoping to just wrap it up into one because I think that should be easy enough to grasp. Okay, so now let's describe the x of the speeder, right? And I think this should be pretty simple because they're moving at constant speed, but that's just whatever the velocity of the speeder is times the whole time, right? They're accelerating over the entire phase from t0 to t2. So that's just t2 minus t0. And because I'm, I always like to keep track. At this point, we have two equations, and I just want to look at how many unknowns we actually have. So xp and xs are equal to each other, but they're an unknown. So I'm going to draw a squiggle for unknown and maybe a regular underbar for known. But velocity naught of the police car, we know that, right? T2 minus T1, we know. Is A what we're trying to find? No, A we are even in fact given, right? A we're given. T2 minus T1 we know. T1 minus T0 we know. And again, V naught P we also know. Velocity of the speeder is something we're trying to find. And T2 minus T naught we also know. So at this point, things are looking pretty good, right? Remember that XP and XS are equal to each other. They're the position after they catch up again after the chase. So at this point, we have basically two unknowns and two equations. So this is totally solvable, right? Two unknowns and two equations. So yeah, I think you should be able to just go hammer through and solve that. At this point, it's just algebra. Sound good?
Yeah, cool.
Okay, I'm going to stop recording there unless you have any last questions.
Nope.
Okay, awesome. Good luck.